Hello all. This is another unit 4 past paper, also from October 2025. So it turns out that for the first time, I think, I've never seen this before, there were two tests for unit 4, and the same goes for unit 5, unit 6, etc. So the first one was ending in /01. I mean, I'm talking about this part over here. Okay, so the test we solved recently was this test, WPH 14/01, but there is also this one, which is /01A, which is different from the one we just saw. So I'm gonna walk you through this paper as well. It's different, so all the questions are different, so I think it's good practice. I don't know why there are two papers for the same unit for the same period, like October 2025, but I guess that's good news for you because you have another test to prepare yourself with. So let's jump straight in with section A. So the first question says the number of neutrons in a nucleus of, that's gold, AU is gold, 197 is, and as we know, the mass number is equal to the number of neutrons plus the number of protons, which is Z. So the number of neutrons is simply A minus Z. So we subtract these two numbers pretty much. And we find 197 minus 79, which is 118. So A is the correct answer. And by the way, without even doing any calculations, you can see that if you look at the answers, I say this in every test that we go through. If you see the answers, okay, 197 is obviously wrong, 79 is obviously wrong, then 276 is too large. So by elimination, you can also arrive at the same correct answer, okay? So, question 2. A particle moving in a circular path completes 7.5 revolutions in 9 seconds. Its angular velocity in radians per second is, so omega is 2 pi times the frequency, and whenever we are given revolutions in some time, that's the frequency, okay? So we have 2 pi times 7.5 revolutions in 9 seconds, and if we work this out, we find 5.24 radians per second, which is option B. Okay. Now question 3. A moving pion decays into two particles Y and Z. This decay occurs at point X in a particle detector, and the tracks observed are shown. Okay. Which of the following is a valid conclusion from these tracks? Option A, momentum has not been conserved. That's erroneously wrong, okay? Because if something like that is observed, you will win a Nobel Prize and physics will be in trouble, or it will need modification or something. So that's obviously wrong. B, the pion is a neutral particle. That's a plausible answer, okay? So we keep that. Because a neutral particle decays into two particles of opposite charges, okay? Y and Z have different masses, and then Z is a negatively charged particle, okay? So the problem with options C and D is that, okay, they are not telling us, but there is a magnetic field in here, which is either out of the page or into the page, okay? So a charged particle in a magnetic field undergoes circular motion with the centripetal force being QVB, okay? And this is gonna be equal to mv squared over r, which is the radius of the curvature, okay? And if we eliminate V, we arrive at r being equal to mass times velocity over q times over b, okay? So we see that the radius depends on the mass and q, so you cannot really tell anything about the mass of the particles or whether Z is the negative or the positive particle, okay? So C and D are wrong, so B is the correct answer. Okay. Okay, let's do question 4. A positron enters a particle accelerator. As it emerges from the accelerator, its mass is measured to be 3.8 times 10 to the negative 29 kilograms. It can be concluded that the positron, okay, immediately you have to think that, okay, the mass of the positron is the same as the mass of the electron. In other words, the mass of the positron is, okay, E plus is the positron. It's 9.11 times 10 to the negative 31 kilograms, right? So this is 100 times heavier, okay? So what happened, it's probably traveling at relativistic speeds, therefore it acquires mass, okay? Or it appears to be heavier, it's the proper way to describe it, because relativistic mass is a very old term used in old school physics. So let's look at the options. A is wrong. Traveling at if the particle was traveling at non-relativistic speeds, its mass would be 9.1 times 10 to the negative 31. B has traveled in a circle, doesn't matter. C, it has become a different particle. Oops, sorry. It has become a different particle. No. So D is traveling at close to the speed of light. Okay. Yes, okay, there is nothing else I want to say here. Let's move to to question 5. Which of the following is an equivalent unit to the Tesla? Okay, so in all of these answers, there is the unit of Newton, amperes, and meters. Okay, so we have to immediately think of the equation FB, okay, BIL. Okay, I mean, there is also QVB, but it's irrelevant to this problem, okay, so we don't use that. So if we solve for B, we see that B is F over, what are we looking for the Tesla? Yes, so B is F over IL, and the units for B, if we use those square brackets that I sometimes use to denote that we are dealing with the unit of each quantity. So, sorry, B is F over I over L, okay? The units for force are newtons, the units for current is amperes, and meters for length, and we immediately see that the correct answer is D, okay? Okay, and question 6. Two capacitors of capacitance 1000 microfarads and 10 microfarads are charged so that they store the same amount of energy. The potential difference PD across the 1000 microfarads capacitor is V1, and the PD across the 10 microfarads capacitor is V2. The value of V1 over V2 squared is, okay, we have to immediately think that the energy stored in a capacitor is given by 1/2 CV squared, okay? Here, the two capacitors store the same energy, therefore 1/2 C1 V1 squared is equal to 1/2 C2 V2 squared, right? So 1/2 goes away. So we need to divide V1 by V2 and then take the square. And then we see that this is proportional to C2, sorry, to, wait. Okay, we need V1 over V2, so which is C2, sorry, over C1. C2 is 10, C1 is 1000, or in other words, 1 over 100, which is 1%, or B. Okay. Question 7. A student suggests that two colliding protons could undergo the interaction shown there, okay? Which of the following statements is true? The resulting particles must have a very high value of kinetic energy. We rarely care about the energy of the resulting particles, so that's wrong. B, the interaction is not possible because charge is not conserved, which is not true, because the charge before is 2, Q before is 2, and Q after is also 2, because we have the positively charged pion and the proton. Okay. C, the colliding protons must have a very high value of kinetic energy. Okay, that's a plausible answer, okay, because the two protons and then the proton and the neutron in the, the proton and the neutron in the right-hand side has about the same mass as two protons, but then we have an extra pion, which means that we needed extra energy to produce that particle, because remember, according to Einstein and observation, energy and mass are equivalent, okay? So we needed some extra energy, okay? So C is a plausible answer. And then D, the interaction is not possible because the number of particles is not conserved. Okay, back in the day, I think, in the very early days of physics, this was a problem because people thought that the number of particles is conserved. We're talking about more than 100 years ago. But then, due to relativity, people concluded that you can change the number of particles in reactions. So C is the correct answer, okay? Moving on to question 8. So a proton accelerates in an electric field and gains kinetic energy, giving it a change in momentum delta P. An alpha particle accelerates in the same electric field and gains the same kinetic energy. The magnitude of the change in momentum of the alpha particle is... Okay, so here we have to think about, okay, the proton has a charge of plus E. So if the electric field is E, then the kinetic energy gained by the proton is, okay, let me write it this way. So the kinetic energy is going to be equal to Q times E, where E is the electric field, and Q is simply E, lowercase e. So the kinetic energy is E times E, okay? But for the alpha particle, the kinetic energy is going to be 2 times E times E, okay? Because it has 2 protons, right? So what's the change in momentum? Just twice the change in momentum of the proton, pretty much, right? So B. I hope this makes sense. So, am I skipping something? No, okay. Question 9. This was one of the rare cases in which I kind of disagree with Edexcel, but we're going to go with their mark scheme because I checked the mark scheme and I was wrong in my answer. So anyway, the graph shows how the magnetic flux passing through a coil varies with time, okay? Which of the following graphs could show how the magnitude of the EMF induced in the coil varies with time? So I immediately answered A, and the reason is that remember that Ampere's law tells you that the EMF is proportional to the change in flux with respect to time, right? So it's pretty much the tangent, the tangent of this curve, right? So I was expecting, since this change in flux with time, magnetic flux, I mean, since it appears to be a parabola, so assuming that phi is proportional to t squared, then I assume that the EMF is proportional to 2 times t, or just t, right? So I was expecting A, but that's wrong. Edexcel claims that the correct answer is B, and you have to think that initially, so answer A tells you that at time 0, the EMF is 0, whereas answer B tells you that at time 0, there is some non-negative EMF present because there is some change in magnetic flux at time t equal to 0. So that's their argument. I'm not sure I agree with it, but okay, we will go with that, okay? But the main takeaway point is you have to remember Ampere's law. And by looking at this, you have to conclude that this is a parabola, therefore the EMF is going to be some straight line, okay? That resembles the equation y equals to cx plus, I'm talking about this one, y equals to cx plus, let's call it m, okay? All right, let's do question 10, the last one in section A. Which of the following is not a valid conclusion from Rutherford's scattering experiment? Option A, the nucleus contains most of the mass of the atom. This was one of the conclusions, actually, okay? B, the nucleus contains protons. Okay, that doesn't sound like one of the conclusions, okay? C, the nucleus must be charged. This was one of the conclusions. And D, the nucleus is very small compared to the atom, which was one of the conclusions. So B is the right answer. Because actually at the time Rutherford hypothesized that there must be something like a particle. He kind of described the neutron or something like that without knowing that the neutron existed. Because don't forget that at the time of Rutherford's experiment, people didn't know about the neutron. I think the experiment took place around 1915, and the neutron was not discovered until 1932, if I'm not mistaken, okay? This is off the top of my head. You can check Google. I don't remember everything by heart, so, okay. Okay, we will now continue with section B, and as you can see, this is kind of a strange paper in that they don't give you an extra space to write. So I don't know what the deal is with this 4A, unit 4, but okay, let's work with what we have. So let's do question 11, part A. State the principle of conservation of momentum. I'm going to use a clean page. Okay, so we can write in the absence of external forces, okay, the sum of all momenta before a collision equals the sum of all momenta after the collision. And we can also write the sum of all momentum before, or I, which means initial, is equal to the sum of all momenta after. And we have to remember that since this is A-level physics, this includes conservation of momentum in both X and Y axis, okay? So let's do part B. A head-on collision occurs between a neutron and a beryllium atom. The nucleus of the beryllium atom absorbs the neutron to form the isotope beryllium 10. And they show you that the neutron and the beryllium travel towards each other before. So this is the situation. And then they show you the beryllium 4 atom, and they don't show you where it moves. I mean the direction of the velocity. So part I, calculate the velocity of the beryllium 10 atom, clearly stating its direction. Okay, so the direction is going to be found algebraically by summing the momentum before. Okay, so let's do part B, part I. So as we said, I mean, we have it over here. The sum of all momenta before should be equal to the sum of all momenta after. So let's start with the sum of all momenta before, which is equal to mass of the neutron, velocity of the neutron. I promised I'm gonna make better letters, so I'm gonna give it an effort, okay? Minus the mass of 9 beryllium times the velocity of, let's call it just beryllium because it's difficult to type. Okay, so this is the sum of all momenta before, okay, because then you can see the picture. This one goes to the right and we take it as positive, and this one goes to the left and we take it as negative, okay? So I'm gonna remove these arrows and let's plug in the numbers. The mass of the neutron is 1.67 times 10 to the negative 27 kilograms times 3,250 meters per second, the velocity, minus 1.5 times 10 to the negative 26 times 175, which is the velocity, yields 2.8 times 10 to the negative 24, and that's kilograms times meters times seconds to the minus 1. Right? So we can come back here. Let's erase this. And it says clearly stating its direction. So the beryllium-10 atom moves to the right. Okay? So you can write it there. So let's write it over here too. Beryllium-10 moves to the right. And this is because the sign came in positive. Okay? Simple as that. Okay, part 2, using a suitable calculation, determine whether the collision was elastic or inelastic. Okay, let's use another clean page. So part 2, we will need to find, wait, we are not done with part I, because it says calculate the velocity of the beryllium-10 atom. What we calculated is the momentum, okay? So the momentum after this part, I'm sorry guys, I don't know why I did that. So the mass of 10 beryllium times the velocity of 10 beryllium is going to be equal to 2.8 times 10 to the negative 24. Therefore, the velocity of beryllium is going to be, if you divide by this value, 1.67 times 10 to the negative 26, you will find, what is it? 167.8 meters per second. Okay? And I also said this to the right. Okay. Now part 2. For the collision to be elastic, we need the total kinetic energy before to be equal to the total kinetic energy after. So the total kinetic energy before is 1/2 mass of the neutron times the velocity of the neutron squared plus 1/2 mass of 9 beryllium times the velocity of 9 beryllium squared. And if we plug in values, we find 9.1 times 10 to the negative 21 joules. Okay, the kinetic energy after is 1/2 the mass of beryllium-10 times the velocity of beryllium-10 squared. And if you plug in numbers, you find 2.4 times 10 to the negative 22 joules, which is less than 9.1 times 10 to the negative 21 joules. So the collision is not elastic, which is something to be expected from this kind of reactions in nuclear physics, where there is an absorption of a particle and then the creation of a new nucleus, etc. I mean, these are things that you are not taught in A-level physics, but in general, that's the case. Okay. Okay. So, question 12. Hammer throwing is an Olympic sport. The sport uses a metal sphere attached to a chain. The athlete holds the chain and spins around to give the sphere a large angular velocity. When the sphere is released, it travels in a parabolic path through the air and lands on the ground. Explain why, at the instant of release, the sphere stops traveling in a circular path. And again, they don't give you any space to respond. So we're going to use a clean page. And let's try to respond to question A. So you can say that the tension of the cable, okay, along with some contribution from the weight component and this weight component that points towards the center of the circle. Okay, because if you take the hammer at some random point, the tension is going to point inwards, but the weight will point down. Therefore, you have to analyze it into a component that is along the radius, okay, along the radial direction. Okay, so the tension of the cable along with some contribution from the weight component provide the centripetal force. Okay, that's why it undergoes circular motion. Okay, at the moment of release, the tension becomes 0. Hence, the hammer flies off. And that's the answer. Okay. Let's go to part B. The sphere has a mass of 7.3 kilograms. The athlete moves the sphere through a circle of radius 1.7 meters. The speed of the sphere at the instant of release is 18 meters per second. Calculate the angular velocity of the sphere. Okay, so part B, part I. So we can simply use V is equal to omega times R. So omega is V over R. So 18 meters per second over 1.7 meters yields 10.6 radians per second. Okay. Part 2, assuming that both the circle and chain are horizontal, calculate the force that the athlete exerts on the chain just before its release. Okay, so this is simpler than it sounds because we know that the centripetal force has to be equal to m omega squared r, and if we plug in values we find 1391.3 newtons. Okay, now we have to go to part C. The diagram below shows the sphere moving in a vertical circle. Okay, so in this direction, I guess. Okay, draw arrows on the diagram in the answer book to show the direction of the centripetal force on the sphere at each of the positions X, Y, and Z. Okay, this is simple because the centripetal force always points towards the center of the circle. Okay, so part I is done. Let's do part 2. The tension in the chain varies as the sphere moves in a vertical circle. State the position X, Y, or Z at which the tension will be maximum and the position X, Y, or Z at which the tension will be a minimum. Explain your answers. Okay, so I'm going to use a clean page and redraw the circle again. Okay, we have the position X, Y, and Z. Okay, let's draw the forces at point X. Since this is a vertical circle, we have two forces, the tension and the weight. Okay, at position Y, we only have the tension. I mean, we only have the tension in the radial direction because we still have gravity pointing down, right? And at the lowest position, Z, we have the tension pointing inwards and the weight pointing down, okay? So at point X, right, we have that T, the tension, plus M times G is equal to M times V squared over R. Therefore, the tension is mv squared over R minus mg. Okay, so that's the minimum value, right? And then at position Y, we don't really need it, but for completeness, let's just write that T is mv squared over R, okay? And at point Z, the tension minus M times G is equal to mv squared over R. Therefore, the tension is mg plus mv squared over R. Therefore, this is a maximum. Okay? And we kind of silently assume that the velocity is constant along this motion. And that's not necessarily the case. But okay, even if the velocity is not totally constant and even if it fluctuates a little bit, the maximum value of tension is going to be at the bottom and the minimum at the top, which kind of makes sense if you ever played with hammers and stuff like that. All right, so this was question 12. We now move on to question 13, which is from linear accelerators and such. And again, you can see that they don't give you any space to provide the answers. But anyway, so 13, part A, high energy particles used to investigate the structure of matter are produced in particle accelerators. The diagram shows the main features of a linear accelerator, also known as a LINAC. Part I, an electron is shown between tubes B and C. The circles in the diagram indicate the terminals of the AC supply, indicate on the diagram their polarity when the electron is between tubes B and C. Okay, so I'm going to write it on the picture we have here, and I'm going to explain. So the polarity is going to be negative on tube B and positive on tube C. Okay, and I'm going to write the explanation in a clean page. So this is part A and part I. So this is tube B, I guess. And this is tube C, is a little bit longer, okay? So the polarity is minus and plus, and we have an electron moving in this direction, okay? And the explanation is that the electron is repelled from B and attracted towards C, okay? Therefore, it accelerates. Okay. Part 2. Explain why it is necessary for the tubes to increase in length along a LINAC. So because this is the answer, okay, because the frequency of the AC supply is constant, the electron needs to spend the same amount of time in each tube, okay, but it moves faster in each successive tube. Therefore, tubes need to get longer. That's the answer. Part 3. The peak voltage of the AC supply is 250 kilovolts. Calculate the increase in kinetic energy in joules as the electron moves from tube A to tube D. Okay, so pretty much you have to count how many acceleration tubes we have from between A to D. So we have 1, 2, 3 acceleration tubes between A and D, right? So the answer is simply, remember that the energy is simply Q times the voltage. So in our case, we have 3 times Q, which is, and the Q is E times the voltage, okay? Because you have the same voltage accelerating the electron 3 times, okay? And if we plug in numbers, we have 3 times 1.6 times 10 to the negative 19 coulombs times 250,000 volts, and we get 1.2 times 10 to the negative 13 joules. All right, part B. The antiproton accelerator at CERN slows down very high energy antiprotons to produce antiatoms such as antihydrogen. By the way, it's one of my interests in this life, I guess. I mean, I would love to work at the antiproton accelerator at CERN. So if you guys are listening to these videos, hire me. I don't know. Okay, I will need some training, I guess, but it sounds like an interesting thing to study. So this is a machine at CERN where they produce, they decelerate, as they say. I mean, they decelerate protons from really high speeds to non-relativistic speeds. So they form anti-atoms like antihydrogen. I think they were also able to form anti-helium, and they tried to study the properties of these anti-atoms. And the catch is that anti-atoms will immediately annihilate with matter, so you have to keep them in magnetic fields. I think in magnetic confinement, they have them spinning around or something like that. But you can go in the web and find about this. It's really interesting, I think. And as far as I know, the properties of antimatter and antiatoms are exactly the same as the properties of matter. They emit the same light, I think, but read more about it. So it says that the diagram is a representation of a hydrogen and an antihydrogen atom. Part I. Use the boxes in the answer book to identify the particles in the antihydrogen atom. So in the nucleus of this antihydrogen, you will have an antiproton, okay, which is negatively charged, I'm sorry. And instead of an electron, we will have a positron. Okay, and that's the answer. Part 2. State one difference and one similarity between the electron and its antiparticles in the antihydrogen atom. Okay, I'm gonna need another clean page. So this is part B, part 2. So the positron, positron has the same mass as the electron, and it has opposite charge than the electron. That's the answer. Part 3. State what will happen if a hydrogen atom collided with an anti-hydrogen atom. And I already said it. It's gonna be a total. Sorry, don't write total. I'm sorry. They will just annihilation. Okay, part C. The proton and the electron are separated by an average distance of 0.053 nanometers. Calculate the magnitude of the electrostatic force acting on the electron at this distance. Okay, this is a simple application of Coulomb's law. So the Coulomb force is going to be K times the charge of the proton, which is E, times the charge of the electron, which is also E, so E squared over R squared. Okay, so we have 8.99 times 10 to the 9. Let me use some units for a change. So all the way to the right, as always. Okay, so K has units of newtons times coulombs to the minus 2 over wait, I'm confused. Times meter squared. Okay, that's the answer. Okay, did I miss something? No. Okay, and then the electron has a charge of 1.6 times 10 to the negative 19 squared, and then you have Coulomb squared. Remember, I pull all the units to the right and all the numbers to the left. Okay, and in the denominator we have 0.053 times 10 to the negative 9 squared, and then we have meters squared. Okay, meters and meters cancel, Coulomb square cancels, and we are left with 8.2 times 10 to the negative 8 newtons. Okay, part 2. Oh, wait, yes, sorry. Part C, part 2. Okay, too many questions. Calculate the electrostatic potential energy of the electron at this distance. Okay. So the electrostatic potential energy, we will denote it as U, capital U, is equal to the charge times the electric potential. And the charge is E. The electric potential is K, E over R. So we get K, E squared over R. And if you plug in numbers, you find 4.34 times 10 to the negative 8 joules. Negative 90, sorry. Okay, let me write this cleanly. 4.34 times 10 to the negative 18 joules. Okay, and now part D. In the early 60s, Murray Gell-Mann proposed a quark model that consisted of 3 quarks. The table gives some of the properties of quarks. Okay, explain what is meant by a charge of plus 2/3. Okay, this is sometimes called as fractional charge. So di, so plus 2/3 simply means 2/3 times E. Okay, the charge of the electron. So I don't think there is anything else to say. So let's look at question number 2. State the predicted mass and charge of the U bar quark. Okay, so the mass is going to be the same as the up quark. So the mass of the U bar is going to be equal to the mass of U. So 4 mV over C squared. And the charge is going to be minus 2/3 E, the opposite. State the predicted mass and charge. Did I mess up something? No. Okay. Good. All right. And then question 3. Calculate the mass of the S bar quark in kilograms. Okay, so they give us the mass in MeVs per C squared. So we have to convert that. So the mass of the S is 80 MeV over C squared. 1 MeV is 10 to the 6 EVs, and then 1 EV is 1.6 times 10 to the negative 19 joules. And then we have C, which is 3 times 10 to the 8 squared. And then we have meter squared second squared. And if we carry the calculation, we will find 1.42 times 10 to the negative 28 kilograms. And that's the answer, and let's move on. This was a long problem. Okay. All right, question 14. The diagram shows a simple generator. It has a flat coil of negligible resistance which can be rotated in a magnetic field. The coil has 500 turns and an area of 2.5 times 10 to the negative 3 meters squared. By the way, just a silly comment, these generators are, machines, I guess, that you can buy and have in your own house. And in fact, in countries where they run low on electricity, I think in South Africa they have some problems. For those of you who are watching from South Africa, say hi. So this is the principle. I mean, there is a machine, like a kerosene machine usually, or I don't know, petrol machine, whatever, that spins this kind of coils inside a magnet, and they produce electricity enough to light up your house in case you run out of electricity. Okay. All right. The graph, let's move on. The graph shows the variation of the magnetic flux linkage N phi with time t as the coil is rotated at a steady frequency in a uniform magnetic field. Okay. Question A, determine the frequency of rotation of the coil. Okay, as you can see, and this does not only have to do with A-level physics, any type of physics or engineering functions, whenever you see something that looks like this, you have to immediately think of sines and cosines. And before I tell you the answer, take a moment to guess whether this is a sine or a cosine. Okay, it's a cosine. And the reason is because times 0, we have a maximum. Because cosine of 0 is 1, whereas sine of 0 is 0, okay? Simple as that. So we know that this is a sinusoidal behavior, as it's called, okay? Right. We have to find the frequency, and this is the frequency from maximum to maximum. Actually, this is the period, sorry. From maximum to maximum, we have, the period is 10 milliseconds, as we see there, okay? So the frequency is 1 over that, okay? So actually, let me use a clean page. So question A, the period is 10 milliseconds. The frequency is 1 over the period. So it's 1 over 10 times 10 to the negative 3, or 100 hertz. Okay. B, determine the magnetic flux density of the field. Okay. So they give you the magnetic flux linkage. Okay. So let's see. So N times phi is equal to NBA, right? But we are interested in B, the magnetic flux density. So you have to solve for that. It's a little bit of a strange problem, it feels, but you will see. So B is N phi over NA. And I'm not deleting this N because we are actually going to use N phi from the graph, okay? And in fact, where is the undo? Over there, okay. And in fact, we will use the N phi maximum, right? So this value over there, or here, okay? So N phi, let's call this max, okay? And this is equal to 2 times 10 to the negative 2 Webers over N. The number of turns is 500. The surface area is, what was it, 2.5 times 10 to the negative 3. So the answer is 0.016 Tesla. Okay, then part C. Determine the maximum EMF induced in the coil. Okay, so the maximum EMF is given by minus dn phi over dt, and we have to find what n phi is. Okay, so n phi is, if we look at the graph, remember I told you earlier that this is a cosine function, so n phi, which we take as a function, is equal to 2 times 10 to the negative 2 times the cosine of omega t. What is omega? 2 pi times the frequency, which is 100, times t. Okay, don't get scared, but if t is 0, notice that we get the cosine of 0, and the cosine of 0 is 1. Therefore, n phi is 2 times 10 to the negative 2 Webers. Okay, if the time is 10 seconds, we will have 2 pi times 1,000, which is 2,000 pi, which is in fact the same as cos of 2 pi, which is also 1. Therefore, we get this value at time equals to 10 milliseconds. Wait, I confused you. I'm sorry. For time equals to 10 milliseconds, we will get 10. We will get cosine of 2 pi, in fact, okay, which is 1. And also again, we get that. And then for time equal to 5, we will get the cosine of pi, which is minus 1. Therefore, we will get 2 minus 2 times 10 to the negative 2. So what I'm trying to say is that this function describes this plot. Okay? And now taking the time derivative of this is really simple, right? So E is simply, we will get rid of the negative sign, we don't need it. E is simply 2 times 10 to the minus 2 times 2 pi times 100 times sine of 2 pi times 100 times t, and I will need another clean page. Therefore, E max happens when when this sine functions and cosine functions only take values between minus 1 and 1. Therefore, the maximum value is 1. So E max is simply 2 times 10 to the negative 2 times 2 pi times 100, which gives you 12.6 volts. Okay? And any comments? No, I think I'm good. We're gonna move on to question 15. A student is investigating capacitance. She sets up the circuit shown below. Okay. Okay. Question A: when the switch is closed, there is a maximum current which decreases to 0 over a period of time as the capacitor charges. Explain why. So, and recall that when we charge a capacitor, the current goes like I naught e to the minus t over tau. So indeed it goes to 0, starting from a maximum. So let's explain it. So due to the variable resistor, comma, there is a current I equal to V over R, initially flowing in the circuit. Okay. Also, the voltage across R is equal to V, but as the capacitor charges, the voltage drops the voltage across R drops, and hence the current in the circuit drops. Eventually, the capacitor gets fully charged and the current drops to 0. Okay. Part B, the student discharged the capacitor. She set the variable resistor to a maximum resistance and closed the switch. As the capacitor charged, the student decreased the resistance of the variable resistor so that the current remained constant until the capacitor was fully charged. A graph of current against time is shown. And a little comment here, I gave this problem, a similar one, to my students back in the day. And people always expect, they try to think of this as an exponential decay curve because this is what they expect. But this is obviously not an exponential decay curve. Therefore, you cannot really use the exponential decay law for the current in this case. And you have to think a little bit more creatively, okay? So, question I, determine the capacitance of the capacitor. Okay, so let's go to the clean page and write that current is charge per time. I mean, that's the ultimate definition, right? So the charge is equal to I times T, which is nothing but the area under the I versus T graph. And this is what I meant by saying thinking creatively. So yes, we have to find that area to find the charge, and once we know the charge, since we know the voltage, we can find the capacitance. So Q is equal to the area of this object that looks like a trapezium, right? And what's the area under? What's the area of a trapezium? Is base 1. So this base plus this base plus the height over 2, right? So let's write this down. So, okay, what is my pen? So, this base is 110, okay? So 110 plus 100 for the second base, which is up there. I keep saying base, it reminds me of baseball. So anyway, I don't know why. Times the height, which is 2.4, right? So times 2.4 times 10 to the negative 3. My handwriting is horrible, I apologize. So times 2.4 times 10 to the minus 3. Don't forget to divide by 2. I forgot when I was solving it. So, and this is coulombs per second times seconds. So the charge, I need another clean page, is 0.25 coulombs. And then we can simply divide charge by voltage to find 0.25 over 6 yields 0.04 farads. Okay. Okay. Hence, determine the energy stored by the capacitor when it is fully charged. Okay, this is part 2, right? I forgot to do this when I was solving the paper myself. So the energy is 1/2 CV squared. So where's my calculator? Over here. So that's 1/2 times 0.04 times 36, because the voltage is 6. So the answer is 0.04 over 2 times 36. So 0.72 joules. Okay, good. Are there any more questions there? No. Okay, let's move to part C. Capacitance can also be determined by measuring the current I at regular time intervals as a capacitor discharges through a resistor and plotting a graph of ln of I against time. Explain how capacitance can be determined using this graph. Okay. Since I is I naught times e to the minus t over tau, we can take the ln of both sides. Ln of I is equal to minus 1 over tau times t plus ln of I naught, which has the form y equals to mx plus c. So the gradient is equal to minus 1 over tau, and since tau is RC, we see immediately that we can find the capacitance, right? Because we have tau is equal to minus 1 over the gradient, and then we see that C is just minus 1 over R times the gradient. Okay, and part 2, a capacitor was discharged through a 390 ohms resistor. The capacitance of the capacitor was calculated at 2200 microfarads. Explain why the data from the graph for this circuit would be difficult to obtain using an ammeter. Your answer should include a calculation. So, okay. We have to find the time constant, which is RC, which is equal to 0.66 seconds. So the capacitor discharges very fast. Oops, again, my handwriting. Capacitor discharges very fast. So the ammeter will be slow to respond. Okay, question 16. A student performs 2 experiments where a heavy swinging object attached to a pivot is raised to a constant height and released, and this is shown in picture A, before striking a stationary ball. The student measures the distance the ball travels across a rough surface before stopping. In the first experiment, the swinging object immediately comes to a stop after striking the ball, which is situation B. In the second experiment, the swinging object can swing freely past the lowest point, which is shown in C. Okay, discuss the expected results of both experiments with reference to both the momentum of the ball and the distance the ball travels before stopping. Assume that the same average force is applied while the object and ball are in contact and that the same ball is used in each time. Okay, this is a strange question, I think, but okay, so we can write things such as the swinging object has the same momentum before the collision in both cases, right? Momentum is conserved in both experiments, right? Oops. okay, the impulse, which is the key for this problem, is equal to the change in momentum. Okay, or in other words, F times delta T is equal to delta P. And this is the key here. We are told that F is the same, the average force is the same in both scenarios. Therefore, we are to assume that delta T is smaller in situation B because the object comes to a stop, whereas delta T is larger in C, okay? So let's write this down. Since in both experiments, I don't know why I keep writing that E in both, I don't know. Now I'm writing B. Okay. Since in both experiments, F average is the same, then delta P is larger in the second experiment okay, as delta T is larger. So delta P is larger for C, I mean the situation C, and the ball will travel the farthest. And that's the answer. Okay. Let's move on to question 17, which is the last one. Okay, so again, I don't know why they put out this Unit 4A test. I don't know if anybody actually took this test, or maybe they put it out there for practice. I don't know, but it's a strange test. It's strange in the sense that they don't give you space to respond to questions, and then they only have 17 problems. They usually have 22 now. I don't know. But anyway, it's an interesting test anyway, and it's very useful for you guys. So, question 17, a teacher is using an electron beam tube to demonstrate the deflection of electrons in a uniform electric field. A potential difference of 4800 volts is applied between the cathode and the anode of the tube. The cathode is heated and electrons are emitted from the surface. These electrons are then accelerated from rest and pass through a hole in the anode. State the name of the process by which electrons are emitted from the cathode. I'm going to respond here. So it's just thermionic emission. Thermionic emission. And it's easy to remember. I mean, in A-level physics, they just give you problems related to thermionic emission. And in AS level physics, they give you problems related to the photoelectric effect. Okay, so it's easy to remember. All right. Part B show that the speed v of the electrons as they leave the anode is about 4 times 10 to the 7 meters per second. So, since we're dealing with electrons, we have that 1/2 mv squared is equal to q times v, which is E times the provided voltage. So I use this symbol V with, I don't know, the weird notation right there to denote the voltage, okay, so you don't get confused. So the velocity of the electrons is simply the square root of 2 times E times the voltage over the mass of the electrons. And if you plug in numbers, you will find 4.11 times 10 to the 7 meters per second, which is about 4 times 10 to the 7 meters per second as requested. Part C. After leaving the anode, the electrons follow a parabolic path as they pass between a pair of parallel plates with a potential difference of 800 volts between them. There is a uniform electric field between the plates. Calculate the force due to the electric field that acts on an electron while it is between the plates. Okay, first of all, we have to find the electric field. I'm going to do it over here. The electric field is V over D. Oops. Okay, maybe I'm going to use a clean page, because if I squeeze myself there, I make really horrible letters. So, part C, question I. The electric field is equal to the voltage over the distance between the plate. I'm talking about this voltage now, okay? And this distance, okay? So this is simply equal to 800 over 0.05, which is 16,000 volts per meter, okay? Which is also equal to newtons per coulomb. I mean, volts per meter are equivalent to newtons per coulomb, okay? And then the force is simply the charge times the electric field, I mean Q times E, right? So 1.6 times 10 to the negative 19 times 16,000 yields 2.56 times 10 to the negative 15 newtons. That's the answer, okay? Question 2. An electron experiences an upward acceleration, A, as it passes between the plates. Its vertical displacement h after time t is given by 1/2 at squared. Calculate the value of h as the electron leaves the plates. And here's the point where I will remind you that it's good to know everything from AS level physics, especially Suvat equations. It's useful, okay? Okay. So for part 2, we have 1/2 at squared, and we don't know either a or t squared. How do we calculate a? We know that the force is equal to mass times acceleration. So the acceleration of the electrons is simply the force over their mass. So 2.56 times 10 to the negative 15 over 9.11 times 10 to the negative 31. And this is simply equal to 2.81 times 10 to the 15 meters per second. And we also need t. How can we find t? We are given this distance 15 centimeters, and we know the initial velocity of the electron. So in the horizontal direction, if we use Suvat equations, and I'm going to remind you the Suvat equations, are they here or here? Okay. So in the horizontal direction, x is u times t plus 1/2 at squared. Do we have an acceleration in the x direction? No, because no force is experienced by the electrons as they move along the x direction. So, and then we substitute this u to v, which is what we calculated over here, this v over there, okay? So that way we can calculate the time, okay? So let's call it x equals to v times t. So t is, what is it, x over v. X is 0.15 meters, which is 15 centimeters, over 4.11 times 10 to the 7. And this is equal to 3.65 times 10 to the negative 9 seconds. So h is equal to 0.019 meters, which is 1.9 centimeters, which makes sense, right? This gap is 5 centimeters. We found 1.9 centimeters, so that sounds good, right? Reasonable. All right. So let's do part D. Keeping the potential difference between the cathode and anode at 4,800 volts, and they are talking about this part now, okay? The potential difference between the parallel plates is decreased, okay? Draw the new path of the electrons on the diagram in the answer book C. Okay, so they mean over there. Label this as path A. Okay, so in this scenario, the electrons will have the same initial velocity as before, so they will take the same amount of time to traverse these 15 centimeters. In other words, they will need 3.65 nanoseconds, as we just found, okay? But the potential difference will be decreased, okay? The potential difference, this potential difference will be decreased. Therefore, they are gonna be deflected by a smaller amount, so they will look like this, I guess. Okay, let's call this path A. Okay, since they want us to use the booklet. Okay. Part 2, keeping the potential difference between the parallel plates at 800 volts, the potential difference between the cathode and anode is decreased. So if we go back here, they now decrease, this value, okay? Which means that now the velocity of the electron beam is gonna be lower. The initial velocity is gonna be lower than before, right? But this means that they will remain between the space. If this initial velocity is lower, then they will spend more time to traverse these 15 centimeters, while the potential between the plates is 800 volts, okay? So what's going to happen in this scenario? The electrons will be deflected more, right? Because they will spend more time, so they will keep bending upwards, okay? So the path in this scenario will look like this, okay? So let's call this, they want us to call it B. Okay, I hope this makes sense. And this was Unit 4A. This is the first time where they have two tests for the same unit. I don't know why this happened, but I think it's good news for you guys because you have more past papers to practice with. I hope these videos are useful as every time. Please like and comment below because it helps with visibility for my videos. I hope they are useful. If you have questions, please ask in the comments. I always reply to comments. And hopefully I will put out more videos soon. I am planning on actually pausing with the lessons a little bit and working only towards past papers. So from what I saw, there is also a Unit 5 from October 2025, and then there is a Unit 5A, which will hopefully be different from Unit 5. So I'm trying to say that I will probably put out more videos with past paper walkthroughs. And then I will go back to the lessons about Unit 1 and Unit 2 that I still haven't finished. So anyway, see you in the next one. Bye.